Hi everyone. Today we'll talk about infinite limits. Let's start by computing a couple of basic ones. The limit of 1 over x as x goes to 0 from the right, and the limit of 1 over x as x goes to 0 from the left. And we'll use tables and graphs to find these limits. Let's start with the table on the left. The inputs get closer and closer to 0 from the right. Let's see what happens to the outputs. Plug in 1 to the formula and you get 1. Plug in 0.1 and you get 1 divided by 0.1, which is the same thing as 1 divided by 1 over 10, which is the same thing as 10. When you plug in 0.01, a similar thing happens. You get 1 divided by 0.01, which is the same thing as 1 divided by 1 over 100, which is the same thing as 100. Then you get 1000 and 10,000. As the inputs get closer to 0 from the right, the outputs grow infinitely large. They tend toward infinity. If you plotted these points on the graph, this is what you would have obtained. If you connected the dots, you would obtain the graph of 1 over x for x's bigger than 0. Now, as the inputs get closer and closer to 0 from the right, the outputs grow without bound. They tend toward infinity. In such cases, when the outputs tend toward infinity, they grow without bound, we say that the limit is infinity. Let's take a look at the table on the right. The inputs are the same as in the first table. Now they just have negative signs in front of them, which means the outputs will be the same, but negative. And I get -1, -10, -100, -1000, and -10,000. As the inputs get closer to 0 from the left, the outputs tend toward negative infinity. Plotting these points confirms it. As the inputs get closer and closer to 0 from the left, the outputs tend toward negative infinity. In that case, we say that the limit is negative infinity. Could you compute or find these limits without seeing the table or without seeing the graph? This is how I like to do it. When I see a function 1 over x, I ask myself, what happens to the numerator and what happens to the denominator? 1 is always 1, so the numerator always stays 1. The denominator gets closer and closer to 0 from the right. These numbers are small but positive. To denote that, I like to put 0 with a little plus in its exponent. This means that the numbers in the denominator are very close to 0 but positive. Now, in the numerator I have a positive number. In the denominator I will also have positive numbers. A positive number divided by a positive number gives me a positive number. What's more, dividing by smaller and smaller numbers gives me bigger and bigger numbers. That's why I have positive infinity as the answer. In the second example, I can do similar type of analysis. In the numerator, I always have 1. In the denominator, I have numbers that get closer and closer to 0 and are negative, so I like to put 0 with a little minus sign in the exponent. This tells me that in the numerator I have a positive number, in the denominator I will always have a negative number, so I know that the answer will be negative. What's more, the numbers in the denominator are close to 0, so 1 divided by numbers close to 0 gives you numbers larger and larger, in this case larger in the negative direction, so I get negative infinity. Let's see if we can apply these ideas to compute a couple of limits, in fact 6 limits. If you would like to do this exercise on your own first, this is a good time to stop the video. You can download these notes using the link in the video description. This time I will try to compute these limits without using a table or a graph, but by using that method of seeing what happens to the numerator and what happens to the denominator. In the first case, the numerator is always 3. That never changes. The denominator gets closer and closer to 0 from the left. So I get a positive number divided by a negative number. That gives me negative. And I know that the denominator gets closer and closer to 0, which makes the whole fraction get bigger and bigger. So I get negative infinity. In the second example, the numerator is always 1. The denominator, as x's get closer and closer to 0 from the left, x squared will also get tiny and tiny, but the square will get rid of the minus. So even though I'm plugging in x's that are close to 0 from the left, such as negative 0.001, that negative will disappear because of the square, which means I will have numbers that get closer and closer to 0 in the denominator but are positive. This gives me positive infinity. In the third case, in the numerator, as numbers get closer and closer to 2 from the right, for example, numbers such as 2.1 or 2.01, 2.001, the numerator gets closer and closer to the value 2 minus 3, which is negative 1. So the numerator tends toward negative 1. The denominator, as I'm using numbers slightly bigger than 2, let's say 2.1, the denominator gets closer and closer to 0, but is positive. 2.1 minus 2 is 0.1. So the numbers in the denominator are positive, but close to 0. So I get negative number divided by a positive number. That gives me negative. And I'm dividing by numbers closer and closer to 0, which gives me infinity. So I get negative infinity as my answer. Let's take a look at the limits on the right side. This time, I take the limit as x goes to 5 from the right. I check what happens to every single term. 1 minus x tends toward 1 minus 5, which is negative 4. So this term gets closer and closer to negative 4. The second term, x plus 3, gets closer and closer to 5 plus 3, which is 8. So the numerator gets closer and closer to negative 4 times 8, which is a negative number. In the denominator, I'm using x's that are slightly bigger than 5, such as 5.1, for example. If I plug in 5.1 to this expression, I definitely get a small number very close to 0, but a negative number. So the denominator gets closer and closer to 0 from the left side. Numerator is negative, denominator is negative. Negative divided by negative gives me positive. Since I'm dividing by numbers closer and closer to 0, I get positive infinity. Let's take a look at the next example. Let's start with the numerator. I'm getting closer to 1 from the left. So the numerator gets closer to 1 squared minus 1 plus 1, which is 1. So I get that the numerator gets closer and closer to 1. In the denominator, when I'm using x's close to 1 but less than 1, because they're coming to 1 from the left, let's say 0.9, when I plug in 0.9 to this expression, I know that 0.9 squared is less than 1. So something less than 1 minus 1 gives me a negative number here. So here I will get a negative number, close to 0. Over here, when I plug in 1, I get closer and closer to 3. So the denominator appears to be of the form 0 with a minus sign times 3. So I get a positive number divided by a negative number. That gives me negative. The denominator gets closer and closer to 0. Note that 0 multiplied by 3, or a number close to 0 multiplied by 3, is still close to 0. So I get negative infinity. In the last case, I have a non-rational function. Let's try to analyze it step by step. I'm getting closer and closer to 4 from the right. That means that this expression gets closer and closer to 2 from the right, but it's always slightly bigger than 2, because square root of 4 is 2, and I'm going to take square roots of numbers slightly bigger than 4, such as 4.1 or 4.2. So this number is getting closer and closer to 2, but is always bigger than 2. So when I subtract 2 from it, that tells me that this number is close to 0, but positive. What happens to the natural log as we plug in numbers closer and closer to 0? To answer that question, you have to remember how natural log function looks like. Here's the y-axis, here's the x-axis, and here's the natural log function. Note that as the x's or the inputs get closer and closer to 0, the outputs go toward negative infinity. So here, the answer is negative infinity. There's just one more thing I want to mention. When we write the limit of f of x as x goes to a equals infinity, does it mean that the limit exists and equals infinity? Or does it mean that the limit does not exist because the values of the function get arbitrarily large as x gets closer to a? The answer is that the first is false and the second thing is true. Remember, a limit is a number. Infinity is not a number. So when people write that the limit is infinity, they say the limit does not exist. It just doesn't exist in a special way. It doesn't exist because the values of the function get arbitrarily large as x gets closer and closer to a.